Hey, how you guys doing? Coming at you with another optics video. That was my phone. Anyways, so today, hopefully the video is not too long, because I feel like a lot of it is just very similar to what we did with just like concave and convex lenses. There's just a couple of like new things that we'll have to memorize. So I'll just go through like some of the math stuff and some of the conceptual stuff. But there's some things from these slides that you just need to go back and just memorize, like play around with the simulation and figure out where, if the object's at a certain place, then the image, where is that going to be, so on and so forth. So we'll talk about that more in a sec. But anyways, so reflections and mirrors. So one of the equations that he wanted us to memorize was this big boy, which basically is, what is the percentage of light that's going to be reflected off a given surface. And so you just plug and chug to get the answer. Cool, that's what that is. And there was like one more thing I forgot to write in here. If you have a surface and light comes in and reflects right here or at a certain point and then goes off this way, and then we have the norm, the angle of incidence and the angle of reflection, those are gonna be the same. So I feel like that's a given, but anyways, so let's talk about concave and convex mirrors. So this first one we have here is concave, and unlike our lenses that are concave, these ones are going to converge light. Concave, converge. And because of that, when we find the power of a concave mirror, it's going to be a positive power. Okay? And so when light comes in, it's going to hit it and then converge at a given point in front of the mirror. Or, we'll figure out later on. That depends on where the object's at. But anyways, and then for a diverging mirror, since the light is diverging, we've got a negative power here. And light's going to go and diverge out. And if we kind of drive back, we have this like diverging point right here that kind of shows where the things are going to go. But yeah, anyways, so there is that. So that's kind of just defining what they are. So another important thing to remember is that if, let's say, light's coming this way, anything that is on this side of the mirror will be real. Okay, and if it's on this side of the mirror behind it, will be virtual. Okay, so that's something to remember when you're doing your equations and all that stuff. Let's say your math comes out kind of wonky and you're like, this object should have been real, but I'm seeing it over here. Or maybe you thought it was supposed to be real, but your math shows it over here. You can kind of use what you understand conceptually to double check your math and vice versa. So yeah, anyways, so there's that. This is importante. So this is our power equation to figure out how much power a mirror has, right? So it'll be negative 2n over r. And typically a mirror is going to be chilling in air, and so it's going to be negative 2 times 1 over r. And we can just think of it as negative 2 over r to be easier. So P equals negative 2 over r. So I've got a couple practice problems. We're going to work through them. It might be a good idea to go back and try some of the practice problems that Dr. Martin posted. So anyways, but let's go ahead and do this real quick. So we have a mirror with a radius of curvature of, this should be negative. Classic me. This should be negative as well. Double classic. Oh my gosh, don't tell my wife. This one should be negative down here. Sue me. Anyways, so we have a mirror concave with a radius of curvature of negative 20. So it's going to be somewhere over here. Bloop. And we have an object that's placed at negative 40 centimeters. So where is the image going to be located? Is it real or virtual, erect or inverted? And what's the magnification, the resulting magnification? So let's quickly just plug and chug. We're going to cruise. So we got the radius of curvature, which will be, if we're trying to find the power, we're going to do -2 over r, because remember, we're in air, so we don't need to worry about n. So -2 divided by a -0.2. That's going to give us a power of a positive 10 diopters. And then we have an object that's at -40, and I promise I can do this in my head. I'm using my calculator. Oh my gosh, 1 divided by 1/4. 2.5, I could have done that. So our object divergence is equal to a -2.5 diopters, okay? So just like how we would with the lens, we're going to take this power that we got for the object and add it to the power that we got for the mirror. So plus a positive 10 diopters. And that's going to give us our image divergence of, my brain is not mathing. I just had this s'more bake that my wife made, and it was delicious. I think I might have diabetes now. So the image divergence is going to be positive 7.5 diopters. So now to find the image location, there's a couple ways you can think about this. So Dr. Pratt, the way he said is always think about which direction the light's going. So once it hits the surface of the mirror and starts going this way again, so light's moving this way, if the object is still moving with the light that way, then we can consider it as positive. So because we're after reflection, we're trying to measure from the mirror now, and we're measuring with light after reflection, that's positive. So that's one way you can think of it. And that goes for light's traveling this way, but if we measure this way, this side will be negative, this side will be positive. So you can think of it that way. So if we were to think of it that way, you could do the distance of the image is equal to 1 over 7.5. This I cannot and will not do in my head. We get a 0.133 repeating meters. And so since it's positive and light after reflection is going this way now, we're going to measure with the direction of light 0.13 meters away, and it should be somewhere in here. Okay? So that's one way you can think of it. Or the book, how the book has it, is when you're trying to find the image location, it says that mirrors kind of invert or kind of do something weedy whack with with the light rays. And because of that, we would do a -1 over 7.5. And this comes from the equation n over li. And so you can do it that way, and you can keep your sign convention how we learned it, right? That way, when we do the math, it's going to come out to be a -0.13333333333. And that will show us that it's over here then, right? So you can think of it either way. Whatever you need to do to get the right answer, do it. But, you know, we're going to talk later about the conceptual stuff. And if you know the conceptual things, that can help kind of double check your math and make sure you're putting the images where it should be according to how, you know, where it should be. Blah, blah, blah. So anyway, so in the end, we get an object, we get an image that is located this 0.133 meters away. Okay, so that's where the image is at. Whether you call that negative or positive, that is up to how you decide to do your math. So he's going to define it in the quiz. Like last time, he said, if it's negative, it's behind the mirror. If it's positive, it's in front. So anyways, just make sure you have it straight in your head. So anyway, so it's on the left side. And based off of what I said before, we know for sure it's going to be real because it's on the left side, right? So we already know it's real. I don't have to do any math for that. And then erect or inverted, and what's the magnification? So typically to find if it's erect or inverted, I'm going to use the magnification to get that. So just like we did with lenses, I'm going to use the object divergence, -40, over the image, what the, -40, -2.5, over the image divergence of a +7.5. And that will give us a magnification of this. So it's minified and it's inverted. Okay? Inverted. Some people are going to hate me because I'm saying this, but I've yet to be proven wrong. If it's real, it's going to be inverted. If it's virtual, it's erect. So, and this applies if you're using a one lens or one reflective surface and the object you're using is real. If that's the case, if it's real, it's going to be inverted. If it's virtual, it's going to be erect. If anyone can find an instance where it's otherwise and prove me wrong, please do. That hasn't happened yet. Anyways, so there's that. We solved that problem. We figured out that the image is located here. We got the magnification. We got that information. Great. So let's move on to the next one. So I'm going to show you two different ways you can solve this next one. The first is going to be based off of just understanding conceptually what is going on. And I'm not going to do any math, and I can tell you exactly where all this stuff is. I haven't done the math before. So where is the image located? Or let me back up. We've got a concave mirror with a radius of curvature of -40 centimeters, and the object is placed at -40 centimeters. Where is the image located? Okay, so I'm just going to write over here. I know it's going to be at -40, so right at the same spot. It's going to be inverted. I know it's going to be real. And I know the magnification is going to be 1.00 or -1.00. So I haven't done any math, so let's do the math real quick and see if I got it right. Okay, so radius of curvature, we're going to use that to find the power. So P equals 2, -2, over -0.4. So we got 2 divided by 0.4. We get a power of +5 diopters. And then we're going to do 1 divided by 0.4 to get the object divergence, which will be a negative. Oh, I gotta sneeze. Please no. Oh man. Holy cow. -2.5 diopters. Then I'm going to add that to get our image divergence of +2.5 diopters. And again, you can do this with either a -n/li to get your distance of your image, or just remember that since light's traveling this way after reflection, this will be positive, this will be negative, whatever you want to do. I'm going to do it this way. So -n1 divided by a +2.5. That's going to be as -0.4. Hold up. That's what we got. So we know the image is there. So now I'm going to figure out if what's the magnification if it's inverted and real. We already know it's real because it's on the left side. Okay. So now I'm going to take the image divergence of -2.5 over +2.5. And we get a -1.00x. Holy cow. We got it right. So the reason I did this type of question is because there's going to be questions on the quiz where if you understand the concepts and understand, if an object is located at this spot, then it should be around this. Then a question could take you 10 seconds compared to maybe a minute and a half. And that could save you time so that you can spend more time on the questions that require more time. So anyways, so there's that. let's talk about a couple of things. I just pulled up over here. So a couple of things that you guys should go back and memorize is these things right here. So what the heck? Oh yeah, okay. So just memorize that if, depending on where the object is located, if it's beyond the focal point. Oh wait, what the heck? These are lenses. Anyways, so here's yeah, you should memorize these things. So here's one of them. So one of them is for a concave mirror, if we have light coming from optical infinity, it is going to focus at the focal point. And this is because of that one rule we learned a while ago, that parallel light before, we'll say reflection now, is associated with the secondary focal point. If we have an object at the focal point, then we know that the light is going to reflect and go parallel. For a convex mirror, light's going to come from infinity, reflect out, and it's going the focal point or the diverging point or whatever you want to call it. It'll be that. It'll be right at the secondary focal point. Okay, so memorize that. Know that. Another spot that you should know, that if it's at the center, predictable ray is the nodal ray. Well, anyways, if it's at the center of curvature, then the light, like for example right here, it's just going to go boink boink and go right back. Boink boink, boink boink. So know that as well. And then there's all these other things where if it's outside of the center of curvature, then it's going to be small. It's going to be teensy, inverted or real. And real. If it's between center of curvature and the focal point, it's going to be larger, inverted and real. And if you're inside the focal point, you're going to be virtual and magnified. Okay? So, and you can see all this stuff if you go back and do the simulation. Let me see if I can find it on here. Go and do this guy. And just play around with it for literally 10 minutes, and you'll have it down. It's not too bad. Another thing to understand is that if it's a convex mirror, the image will always be virtual and minified, I believe. You guys can go double check, but right here. Virtual, image is smaller, and erect. Oh, wait, it's a virtual object. Okay, yeah, real object for this, it's always going to be that. And then he goes on to talk about virtual objects. This is where my one rule before gets kind of flippity-floppity. So I said before that if you have a real object, then the image that is real will always be inverted, and the image that is virtual will always be erect. If you're using a virtual object, then the conjugate image, that rule is flopped. Okay? And so if you have a virtual object, your virtual image, your conjugate image, if it's virtual, will be inverted, and if it's real, will be erect. So that's where it gets kind of funky. Just remember, if it's a real object, anyway, we'll just go back and listen to what I said before. But yeah, anyway, so memorize these. Understand that, depending on where the object is placed, what kind of image will be produced. And then make sure that you memorize or understand just a couple of things about radioscopy, this right here, keratometry, just like the basics. Don't go crazy, because I'm sure there's going to be something that comes up about if it's flatter than K, so on and so forth, or whatever. I still need to study these. Anyways, Purkinje images, IOL, corneal inlay, Purkinje. I don't remember going over this. Anyway, so that's that. If you guys have any questions, feel free to reach out to me. Please reach out to me sooner rather than later, because as we get closer to finals, I will not have time to help everyone if a lot of people are asking me. And I won't have time to do multiple group sessions or review sessions. And then for the final review, I'm hoping for it to be just that, a review. It's not going to be a place to learn things, but hopefully a place where you can figure out where maybe the holes are at in your understanding, and then you'll have a couple days to mend those holes so that you're not confused for the final. But we'll talk about it more at the final review, what to watch out for the final. But anyways, good luck. Thank you.